Hi, today we will talk about what is B-tree and how is it used in database indexing. Let's see an example. A B-tree is a self-balanced search tree, and every node contains multiple keys. We can see all the leaf nodes are at the same level, and every node it can have at maximum 3 keys. So that's the difference with binary search tree. For binary search tree, one node has only 1 key. And the number of keys for a node depends on the order of B-tree. So let's see what's the order of B-tree. So let's see a detailed node. In this node, there are 3 keys, and there are 4 children. So the keys, the key values are sorted, and for this key 30, its left children, all the keys in the left tree are smaller than 30. And for this children between 30 and 70, so for all the key values which are between 30 and 70, it will be in this children. So the keys in a node act like separators. Separators separate two different children. If there are 3 keys, then it will have 4 children. Now we can understand that the number of keys for a node depends on the order of B-tree. Every B-tree has an order. So here B-tree of order 4 contains a maximum of 3 key values in a node and a maximum of 4 children for a node. For B-tree, there are some properties. Property 1, all leaf nodes must be at same level. And property 2, a non-leaf node with n-1 keys must have n number of children. So the keys act like separators. So n-1 keys means it have n number of children. Property 3, all the key values in a node must be in ascending order. And for every key, the keys in left tree are smaller than it. The keys in right tree are larger than it. So this rule applies to all the keys. Property 4, if the root node is a non-leaf node, then it must have at least 2 children. If it's a non-leaf node, then it must have children. So why at least 2 children? We will look at this property when we try to constructing a new tree. Property 5, all nodes except root must have at least m divided by 2 minus 1 keys and maximum of m minus 1 keys. So m here is the order of B-tree. So this maximum of m minus 1 keys, this one we can understand. So how to understand this, at least the number of keys, also we will look at it later. Let's see one example how to construct a B-tree. Let's try to insert in numbers from 1 to 10 to construct a B-tree of order 3. So we need to remember in a B-tree, a new element must be added only at the leaf node. So we will use this rule when we are inserting new elements. So insert 1. There's no root, so we need to create a root node with 2 keys and put 1 to this first key. And insert 2, we find the root node is also the leaf node, and 2 is larger than 1, so we put 2 here. Insert 3, the root node is also the leaf node, and when we try to insert 3, we find this node there's no empty position, so we need to send the middle value to its parent node. But there's no parent node, so we need to create a parent node. This new parent node will be at root. And for this 3, we need to create a new leaf node. So here is the result after split. 2 is the new root node, and 3 is the new leaf node. And the right children of 2 pointed to this new leaf node. Here, we can understand this property better. If the root node is a non-leaf node, then it must have at least 2 children. If it's a non-leaf node, means it has splitted. So after split, it has at least 2 children. Insert 4. So 4 is larger than 2. Then we find its right node, and it's a leaf node, and there is an empty position. So we put 4 here. We insert 5. We will find this node is also the leaf node, and 5 is larger than 4, but there's no empty position, so we need to send the middle value 4 to its parent node. So parent node has an empty position for it, and for the 5, we will create a new leaf node for it. So this is the result. After split, it looks like this one. Insert 6. We will find 6 is larger than 4. We will find this node. It's also a leaf node, and 6 is larger than 5. So we will need to insert to this node, and it also has an empty position. So we will insert 6 into this node. Insert 7. We also find this node, and 7 is larger than 6, but there's no empty position here. We need to send the middle value 6 to its parent node, and also parent node there's no empty position. So we also need to send the middle value 4 to a new parent node. And for 6, we will create a new node for 6, and 7, we also create a new leaf node for 7. So this is how the tree looks like after split. Insert 8. So 8 is larger than 4, so we find this node, and 8 is larger than 6, so we will find this node, and there's an empty position here, so we input 8 here. Insert 9. Insert 9, and 9, there's no position here, so we will send 8 to its parent. So here is how it looks like. So at last, insert 10. We'll find the leaf node here, and we will insert 10 here because there's an empty position here. Yeah, this is an insertion process when constructing a new B tree. Now let's try to understand this property better. All nodes except root must have at least m divided by 2 minus 1 keys. So m is the order of B tree. So in this example, we can see this is a B tree of order 3. So every time when there's m keys, when we try to insert the m's keys into a node, there's a split occurred. And when split, we will divide these m keys and send the middle value to its parent. So m divided by 2 means the split, and minus 1 means sending the middle value to its parent. So we can understand that all the internal nodes must have at least m divided by 2 minus 1 keys. So let's see how B-tree is used in database indexing. Let's see this example of a table. This user table, for example, there are 600 users. So we'll try to look up a user ID with 251. So we need to check the record one by one. So a data is stored in disk, and if for a large table, it will be stored in different pages. So we need to read one page at a time. Read the page from disk into memory and check the value. So we'll need to read the page from disk one by one until we find the specific user. So database indexing is used here to reduce the number of pages we need to read from disk. So for example, if there is database indexing used, how to look up the specific user. Let's say this is a B-tree. B-tree is used at database indexing. And for one node, there are 5 kids, so it will have 6 children. One node is actually a page in disk. So first we will read the root node from a disk to memory, and we will find the user ID with 251 is between 260, 200 and 300. So we will use this pointer. This pointer is pointed to another node. So it's another page. Then we will read this page from disk to memory, and we will find the pointer here. So 251 is between 250 and 270. So we will find this node. We will read this page from disk to memory, and we will find the exact user 251 and with its record value. So here we can see by using B-tree, we reduced the number of pages to read from disk. So this is how database indexing works. So in today's video, we have talked about what is B-tree and how is it used in database indexing. Thanks for your watching. Bye bye.